Okay, so hello everyone. My name is Eran, and today I will talk about something that we're working on in joint work by Yonatan Sharabi, Alex Dikopoltsev, Mark Lubarov, Yaakov Lumer, under Moti Segev. It's called Photonic time crystal. I will now explain what it means. We work on it theoretically and experimentally. Okay, so our main motivation are crystals, simple crystals, everybody knows, repeating structure. They have interesting gaps that are very useful in many applications, quantum sources, and etc. And also they can form spontaneously in nature. Now they have a photonic counterpart for photons, which are artificial structures that are mimicking this kind of band gap behavior, but in order to do so, they have to be in the right scale. So the changes in the index of refraction should be at the length of the wavelength, and the scale should be on the order of 1 to have significant reflections at each interaction. Okay, so if a pulse experiences the time crystal and it has a spectrum in the band, then it will simply split twice at in the insert and the output of the crystal, and the energy will not increase overall. However, if the pulse is in the gap, then the wave will exponentially increase in energy. This is because there's a just like in a frequency gap where there's an exponentially decaying solution, here because energy is not conserved, the exponentially increasing solution is also valid, and you can get this kind of phenomena. So we quantize the wave equations in this model to see what happens for photons in spontaneous emission and Cherenkov radiation and so forth. So here's our quantum Hamiltonian, and we also have a Floquet-Fermi golden rule that can give us some knowledge about the emission. And first of all, we look at a sample that is completely homogeneous, and what we see is spontaneous emission of photons in the gap from the quantum noise. So what happens is that the quantum noise simply enhances in the photonic momentum gaps, and we get an increase of production of pairs of photons that are entangled because of this phenomena. And if we're in the band, then nothing happens for these photons. Importantly, what we do to get this equation is we use k, the momentum, as the good quantum number. So this is kind of a trick that simplifies the calculation, and it gives us a good intuition towards our simulation and experiments. Okay, so what happens if we put a quantum source in a photonic time crystal like this? So again, if the source, now we can choose the source to have a spectrum in every place in the dispersion. So if the source is in the gap, we again get the exponential growth, but this time in the emission of photons from the source. And there are several other options, like in the band, where we get linear growth, and oscillations if we're not in the band or not in the gap. This is, of course, an extended source, so it will have a specific k and not in all k's. If it's as a point source, then it will always exponentially emit, because the point source have waves in a lot of k's, different k's. And also we studied the radiation of electrons from when they move fast in this structure. So we add this interaction term, and what we see is that we get 3 types of photon emitted from these electrons. We get the Cherenkov electrons from the fact that the electron is moving fast enough, Cherenkov photons, and we get emission from the gap, again spontaneous emission that is enhanced by this radiation of the electron. And the third kind of photons that we get are photons that get some kind of contribution to their momentum from the frequency gaps. So here are the mapping of them, and therefore we get several different photons from this phenomena. So here you can see in these circles, so the orange circles are the gaps, and the green one is the Cherenkov curve, and the harmonics are the purple, and all the interaction between the different curves give different kind of emission. Before I go to the experiments, we also study the topological phases. Actually, these are bands, so they can have a topological phase. And we study what is the relation between the topological phase of the band, the winding of the phase of the the wave function and the spontaneous emission of photons from the material. And we see that actually this topological phase is related to the sign of the phase between the two photons that are emitted in these structures. So if you have a winding band and a non-winding band, then photons in their gap, the phase of the sign between them, the sign of the phase between them will be dictated by this topology. Okay, now what we are doing to make this happen in the lab. So we actually have an experimental platform that we constructed to demonstrate and show this, see this phenomena. So we use new materials that were not available in the past. I mean, they were available, but nobody knew that they behave in such a way. So these are these materials which have epsilon that crosses the zero line at this point, where the shaded red region. And near this point, apparently, if there are certain materials that are fabricated by our collaborators or other groups, then they have a very, very strong change in the index of refraction if a pump pulse hits them. So here you can see a measurement done in our lab where the reflection from this kind of sample is changed by 40% when a pump is hitting it. So the index of refraction here changes by about 20%, and it's very, very strong change and very fast, because also these are femtosecond pulses. But in order to get to this regime where we have the photonic time crystal, we got to go to the extreme, and we actually shrink the pulse further to be single cycle pulse. So it's about 4 femtosecond, 5 femtosecond pulses. And we also measure, and we see these large changes in the index of refraction of about 10%, and we're still pursuing more in the reflection and transmission. When a very, very short pulse that is shorter than the time period of the probe. So this is why this phenomena happens. The time scales are very important, and the strength of the pulse. So we are now doing the experiments also. These are initial results. And to summarize, we have new physics on light-matter interaction. For example, amplified spontaneous emission in the momentum gap. We have new features with free electrons, topological aspects in these structures, and interactions with disorder, which I did not have time to go through, but now we have a PRL published, accepted, so you can read it there. So thank you very much.
Thank you, Eran. We're right on time, so we have enough time for questions. Nathaniel.
I'm not sure why you call this a time crystal. At least in the condensed matter community, what we call time crystal is voting.
You may call it
Let me finish the question. So what we call a time crystal is a system that breaks time compensation spontaneously. And what you have is a time lattice, so you break it explicitly.
Okay, so okay, so the reason is very straightforward. So it's exactly analogous to a crystal, which is spontaneously formed in nature usually, and a photonic crystal, which is artificially formed. So exactly the same analogy. We call it time crystal is spontaneously formed, as you mentioned, in many works. And we do an artificial structure which changes in time periodically like this. So yes, exactly like photonic crystal. Photonic crystal is.
Call it whatever you want, but
yeah. So it's exactly analogous.
Calling something a time crystal means something very specific, and that's not what you want.
When Frank Wilczek,
But you can call it whatever you want.
it's just terminology. But when Frank Wilczek gave the name, we just forgot that this phenomenon was discovered in nonlinear optics. We call it modulation instability, and formation of a train of
You don't even have to know. You can go to the swing in the park here, and you know. If you rock the swing at the omega, you will see that you get an
Listen, what I'm saying is spontaneously, what Frank Wilczek discovered is not only nonlinear optics.
The difference is whether a system can
by itself, by nonlinear.
We can keep fighting on this, how to call these crystals
I don't care.
over lunch.
Let's
Okay? But let's continue with the scientific questions. How to call a scientific phenomena, but with the scientific question. Any more scientific? Yes. Oh.
So What is the energy cost of changing the refractive index? Can you measure it? Does it also exponentially increase?
Okay, so in principle, we do not care about, so we have the pump probe. We do not care about it. It loses a lot of energy, of course, when it changes the index of refraction. But what experiences this photonic time crystal is a different pulse. It's a probe pulse. So in our model, the change is completely external. We do not care about this. But of course, if you would change it a lot and a lot of photons will be created, it will saturate, and eventually the changes will be slower. I mean, that's what we assume, but we did not check it or anything.
More questions? Yes.
When you show this exponential growth in signal, so what is if you just change the index of refraction, what is the source of the increasing the energy?
So the temporal change in the index of refraction, even if it's homogeneous, it actually feeds energy into the wave if it's in a specific band gap. So a similar situation in maybe nonlinear optics, where you can change in a very harmonic time constant way the material, and energy can be fed into another frequency. Here the change is very, very sharp, and it actually makes a broad gap in momentum. In this gap, the wave can get energy from the modulation. So you modulate, and it feeds energy into like a swing, basically.
Any more questions? So just to that point that was just asked, you are basically drawing energy from the modulation or from the excitation that you excite this crystal. We don't have any energy up here from you.
No.
Not yet. Just to make sure. Okay. Any more questions? So we can thank Eran again. And